School of Mines, Dhanbad. Before joining this institute, he was a lecturer in the Department of Computer Science and Engineering, NIT, Jamshedpur, from April 2011 to December 2011. He received his BTech degree in Computer Science and Engineering from Government College of Engineering and Textile Technology, Behrampur, India, in 2006. He did his PhD in Computer Science and Engineering from IIT ISM Dhanbad in 2011, and he has more than 9 years of teaching and research experience. He has contributed over 90 research papers in several journals and conference proceedings of national and international reputations. His main research interests include data compression, multimedia security, and content-based image retrieval. He has organized several FDPs in the areas of image processing and cryptography. He has served as a advisor committee member and technical program committee member in various conferences and workshops. So that was the brief introduction of our today professor. Now I will hand over this session to our sir. Sir, you can proceed now.
Thank you, Aryabhata. So, is there any kind of screen is coming or something?
Yes, sir. Sir, you have to move that screen.
Now is it fine? No.
Yes.
Yes.
Thank you.
Fine.
So, welcome to all the participants. Today, I basically discuss about the multimedia cyber security, and here we basically discuss what way you can protect the multimedia content like images. Okay, so this particular topics I basically want to cover in today's lecture. So here my objective is to present this particular lecture in what way, the different way we can protect the images. So first of all, we basically discuss that image crypto system. So that is the one of the way to protect the confidentiality property of the image content. And subsequently, basically discuss another area that is called the robust watermarking. And the main objective of a robust watermarking is to protect the copyright. Okay. So what is the motivation behind the robust watermarking, and what we can design a particular scheme that I want to show you. And finally, I want to present another area that is called the image forensic, digital image forensics. So there you basically see this particular area in two aspects. One is called the active forensics, that is basically known as a fragile watermarking, and another is the passive forensics. And there, passive forensic can be done in a several ways. Here we basically discuss one of the area, that is the copy move forgery area. That particular how the copy move forgery can be identified in this particular process. That particular things we basically discuss in this lecture. Okay. As you know that that image is one of the common multimedia tools that is widely used in different kind of applications. Now, in this regards, the problem is that that due to the presence of sophisticated image processing tools like image editing tools, this is quite easy to modify the content, redistribute the content, and that means that content can be easily changed in this particular process. Now, therefore, we need certain kind of mechanism so that we can protect the content. You can identify if there is some kind of modifications happened in this particular content or not. So these kind of things can be addressed in this particular lecture. So first of all, we basically discuss one of the area that is called the image crypto system. Now, you people may think about already there is a cryptography is there. So cryptography basically, as you know, that that is one of the way to protect the content. Okay, now cryptography have a different kind of objectives. What kind of security services can be provided based on the cryptography? You know that that it basically provides the security in a three aspect, that is called the CIA. C stands for confidentiality, integrity, and availability of authentication. Okay, now although there is a certain cryptography techniques is there, like if you think about like a symmetric or asymmetric crypto systems, already there is a standard encryption algorithm is there. So then why you need some another crypto system? Okay, so that is the one of the area we basically want to discuss in this particular process. Like in this particular process, if you see this particular image, here this particular image was encrypted by AES algorithm. And as you know that AES is one of the standard algorithm, and still now there is no security flaw with respect to the AES. Okay, so that means AES is basically considered one of the secure algorithm. Even if you apply the AES in this particular algorithm in this kind of images, so here the direct outcome will be like this. So naturally you can think about that such kind of outcome is not acceptable. Okay, but AES is basically secure, and statistically it has observed that that it basically preserves the abeliancy effect. Abeliancy effect means if you change the single bit of the content, there will be drastic changes. So that means still this particular things is not happening in this particular process. Now, what is the reason? The reason is that that we basically apply the image encryption process in a block level, and we know that the AES basically works in the 128 bits. So accordingly, what happened? The image have a homogeneous region. So that means the same regions will be encrypted by the similar way. Now you people may tell that, so then if he basically takes the different kind of mode of crypto system, then it can solve this particular problem. Now the problem is that images in the data like images is quite large. So that means if we apply the AES like algorithm in a directly such kind of large volume of data, so then it is a time consuming process. So, and even it is not required to encipher the particular content in a that way. So that means we have to think about some different way, how can we protect the image content. Okay, so this way you can say that encryption of images, video with standard data cipher directly is time consuming and not suitable for real-time applications. In images, pixels are highly correlated and visual parts of the encrypted image should be removed as well. So it is not possible in this particular aspect. So therefore, we need some kind of suitable image crypto system. Okay. So here, the different kind of technique is basically used for the enciphering the image data. So it may be like a data stream encryptions, multimedia scrambling. That means you can supple the content. Web perturbation. That means we basically transform the image into another domain, like it may be the DCT, DWT, discrete transform, and there we basically change the coefficient value. That is the one of the way. Another way is the bit plane based image encryption. So that means you divide the image into different kind of planes. As you know that image is basically the representation of a pixels, and pixel is having the 8-bit information. So that means if you consider the each bit information one by one, and basis on that if you form the image, so that is called the one of the bit plane. So that means you can apply that enciphering process in a bit plane level. And another is the chaos based encryption, and people are basically prefer the chaos based encryption. Okay, and why the chaos based encryption is more popular? Now it basically we can create the suppling and diffusion process more quite easy way. And here the advantage is like that. Here it basically provides a seed value, and that basis on the seed value, the chaotic map basically produces a pseudo-random sequence, and that pseudo-random sequence is basically used for the enciphering of the large volume of data. Okay, now here the seed value will be considered as a cryptographic key. So based on the seed value, you can create your sequence, pseudo-random sequence as per your requirement. Okay, so there you have a basically different kind of chaotic map is there. Like one of the chaotic map is the logistic map, sign map, ID infinite collapse maps, logistic map, 2D chaotic maps, Hanon map, all are the some well standard chaotic map is there. Now, what will be the way the image enciphering process will be carried out? Now, in this particular process, so this is the one of the conventional way. That means just a minute. My cursor is visible. Is it visible?
Yes, sir. Yes, sir.
Okay.
It is visible.
So that means yes. So here we basically give the image as a plain text, and that particular plain text we basically shuffle in this particular confusion process. So confusion process basically shuffle the content. Okay. Now subsequently, after this particular process is iterated, suppose T1 times. Now here after that we basically perform the substitution process, and that is known as a diffusion, and this particular process will be carried out suppose T2 times. So that means overall that will be executed T1 into T2 times, and finally you will get the one of your desired cipher image. So that is the basically one of the way we basically perform the image crypto system. We basically design the image crypto system. That means you take the image, you shuffle the content using some chaotic maps, then you can use a suitable substitution mechanism, and this particular process will be carried out T1 into T2 times, and finally you get the cipher image. Now here I basically want to show you one of the works that is basically based on the DNA planes. Okay, that means in the current scenario, the DNA is one of the effective way to store the large volume of data. So if you use the DNA concept in a enciphering process, so indirectly what happened, you can store the content in a more concise way, and the event is that the DNA basically gives a more effective security. Okay. And here we basically propose the particular algorithm in this way. That means instead of applying the crypto system, applying the enciphering the whole, directing the whole image, we basically decompose the image into different planes, and that basically planes is nothing but the DNA planes. And thereafter we basically apply our algorithms to encipher this particular content. Okay, so let's see this particular works. Now we basically know that the DNA have a standard DNA stands for deoxyribonucleic acid, and here is basically DNA is basically represented by the four DNA codons, that is ATGC, that is ATGC, and these particular codons are present in a complement way. That means A complement should be T and G complement should be C, like this. So in this particular process, what happened now, we basically defined some value ATGC, and suppose the value is like this 00, 01, 10, and 11. So 00 complement is 11, so that's why A and T. Okay, a 01 complement is 10, so that is GC. So that means if suppose you are following this this binary indexing, so that means A will be mapped to 00 and T will be mapped to 1. So there is a possible way you can do such kind of coding. Like suppose you are considering the rule 6. So rule 6, what happened? Now G will be represented by 00. Okay, and ATGC. So that is 00. 80 that 80 ATGC, that means 80 and 00, and C will be represented by 11, and it is represented by 01, and it is represented by 10. So that means these two are complement to each other, and these two are complement to each other. Okay, so there basically this is called the Watson-Crick complement rules, and here we have this kind of 8 rules are there. Now subsequently, if suppose you have a value like a 0, so that means you are basically following the rule 1. So that means 0 stands for A, and 3 stands for T, and 1 stands for C, and 2 stands for 1. Suppose you are using the rule 6. In that particular case, I can use A stands for 2, because here rule 6, what happened? I basically use the A. So A is mapped to 2. So that means I can say it is a 2, and C is basically mapped to 3. So that's why I have written here 3, and that is your G. G is mapped to 0. So that's why I written as a 1, and C is mapped to 3. So that's it is ATGC. So that means 3 is mapped to 3. So that means T is mapped to 1. So that we have written as a 1. So that is the decoding route in this particular process. Okay, so this is called the Watson-Crick complement rules. Now, what is the limitation of the existing crypto system? So most of the existing image crypto system follow a large number of iterations. Like we have seen that we have to execute the confusion diffusion process. And if suppose we are executing the confusion T1 times and diffusion of the T2 times, so overall you have to perform the T1 into T2 times. So most of the existing image crypto system follow a large number of iterations. That is the one of the, it basically involves a huge computational overhead. Second thing is that DNA-based image crypto system is basically having the 8 rules, but most of the crypto system basically use the only one particular rules. So that means they basically not using the DNA encoding in a proper way. So that means if you can use all the possible combination encoding rules, so that means it will be basically gives the indirect way more security. So that particular thing. So that means in this our algorithm, instead of consider the only particular encoding rules, we have basically selected the multiple all possible encoding rules. So that means it basically indirectly it gives the more security. So that is the one of the objective behind this particular works. Now here the conventional DNA having this kind of operation like a DNA addition, DNA subtraction, DNA XOR or DNA complement. So these 4 operations we basically perform in this particular process. We have another works there. I will basically propose that how we can add some more operations with respect to DNA. So that particular things I'm not going to present here. If you are interested, you can go through that particular paper is available in the website. So now this is the one of the architecture we have basically followed. Now what happened? Now here initially you have taken the image, and this particular image was pre-processed, but you can consider you have done some masking. So that means instead of taking the original image as it is, we have basically done certain kind of masking. So that is masking is basically performed based on the one of the keyless operation. That means a initial vector will be considered, and basis on this particular vector, we basically encipher this content, and that will give some kind of such kind of intermediate results. Now here we basically perform the confusion operation. This is the T1 times, and finally we have performed the diffusion times, and that is only 1 times. So that means we have not included this particular T2 times. So that means overall this particular process will be executed only the T1 times, and finally you will get the cipher image. Okay, so this is the basically steps in this particular process. So that means you have taken the image, and then you have taken one marks. Okay, and this particular marks is basically is a predefined key will be used, but it is basically keyless. And then you just simply perform the XOR, and you will get the intermediate results. Such kind of intermediate results you will get it. Now what happened? We basically perform the ACM annual transformation, and then you get this kind of confused data. And this particular data will be divided into multiple planes, and accordingly you will get the DNA planes. And now from this particular, and in this particular project, one of the interesting thing is that we basically consider the 256 key, but typically this particular image size is 512 by 512. So that means actual volume of this particular image is 5 into 12 into 512 into 8. So this is a huge volume. Like if you're using the AES algorithm. So AES algorithm, what happened? Now we have a 128-bit data, and accordingly you basically select what your key site. So that means for every blocks we basically have a predefined key, but here the data is a huge. And if you use that, and earlier what happened, the previous problem you have seen that the reason of that you are not getting the satisfactory result is that you are using the same key, and the, as per the nature of the image content, that you have a more similar content will be present. Okay, so that's why you are getting the similar kind of, that means the same ciphertext will be present, and accordingly you're getting some kind of meaning there. But here what happened, we basically have a 256 key, and that 256 key will be supple will be transformed to create a large volume of key space, and that key space will be like this. So that means you have this kind of planes will be there, and this particular planes will be used to exert this particular planes, and finally you will get this kind of cipher image. So that is the motivation. So that means in this particular work, so what is the motivation in this? Just a 1 minute. So in this particular work, what is the motivation? The first motivation is that we need a one key scheduling algorithm, because we are using the 256 bits of key, and that key will be transformed to the large volume of key. So we need a key scheduling algorithm. That is the first motivation. Second motivation is that we need, if you can reduce the number of iteration here, because the confusion diffusion will be executed the multiple times, and here if you can reduce the number of iteration, that will reduce the computation overhead without compromising your security. So that is the one of the area. So here we also done these things. That means we have executed multiple times confusion process, but diffusion process we executed only the single times. Okay. Further here, what happened? We have performed the operation in a DNA level. Okay. So DNA plane, if you can perform the operation, so there is another way. That means you can use the DNA property in a more effective way, because DNA having the more parallel processing is quite effective way can execute. So that means in future the DNA based computing can be effectively use such kind of algorithms. And finally you get this particular cipher image. Okay, so let's see what is the algorithms, more details, the algorithm process. Now here we have used the 2D logistic sign coupling maps, and that is not the major concern. You can choose your appropriate logistic map as per your requirement. And here we have used this kind of masking process. So that means we have taken a constant vector from 0 to 255, and repeatedly in a raster scan order we have mapped this particular vector, and we created one large size of vector as per your size equivalent to your input image. And here we have used this annual cat maps to confuse this particular process. And this is the annual cat map operations. And this is the diffusion process in this particular process. That means you have taken the suppled image after the annual cat map, that you have taken the bit permutation. Then you have performed the DNA encodings. And the DNA encoding, we basically select the multiple encoding rules, DNA encoding rules as per the predefine the logistic maps. Okay, and subsequently you have performed the exon and you obtain the DNA plane, and this is if you perform the DNA decoding, and then you can see the image in the real field, and that will get this particular image will not convey any kind of information. So this is basically the results, and here we basically tested our algorithm in a two kind of data sets. One is the natural images and the medical data sets. And here the medical data sets, we are getting such kind of outcome. So this is the images, and this is the image when you have taken the image size of 256 by 256. And this is the another image. All the image having size is 500 kilo by 500 kilo. Okay. Now here we have basically done some analysis. Because the designing of the crypto system is not only the goal. We have to also perform certain kind of analysis to show that whether your crypto system is perfectly secure or not. So first of all, we've done the key sensitivity analysis. Key sensitivity analysis means if you take the single bit of the cipher image, so it will be drastically change your content of your image. Means if you change the amount of change in the cipher image will be large with respect to a single bit of content of your plain text by your key. So this is the measures, and ideal value should be 50% in this particular process. So here this is the image, and this is the one of the particular plane histogram. So that means we can see that there you have a more homogeneity. So that means this is the homogeneous region. But in an encryption process, all the homogeneous was perfectly encrypted in this particular process. So that means this is the histogram shows that all the pixels are uniformly distributed. So that means here you are unable to perform any kind of statistical analysis to predict the original content. Okay, and we also perform the entropy analysis. If your entropy is high, so that means it is more random. So in this particular process, the typical entropy should be in natural images should be 8, and here we have basically seen that we can achieve the close to 8 in all the cases. And histogram analysis, already I have discussed that histogram basically represents the what is the distribution of your pixels, and if the pixels are coming in a homogeneous, so that means it is more secure. That means here you are unable to perform any kind of statistical analysis in this kind of images. Now correlation images, so that means if you take the original image, the pixel correlation, you have a such kind of things. But if you take these particular things, here the correlation value is scattered in throughout the region. So that means it is preserved the correlation, and if the correlation is close to 0, so that means it is be highly secure in this particular process. And we also tested our algorithm in a natural images, and we achieved the effective results, and it is comparable to the all the existing literature work. Okay, so what is the motivation in this particular? Now what is the contribution? Now here confusion is done using the annual cut map. Confusion pixel level permutation is used, and we have used the DNA level XOR operation, and we have used the all 8 DNA encoding rules, and only one round of entire process enough to generate the secure cipher image. The crypto system process all the required security test parameters. That is a very important importance. Whenever you design any crypto system, you also test whether it is satisfying all the security parameters or not. Okay, so this is the particular cases the property DNA molecules can be applied. So what is the way you can explore this particular area? That means the DNA molecules can be applied in image to design a crypto system, which can be more effective compared to the conventional crypto systems. The proposed crypto use all the 8 possible DNA encoding rules, so that's why it is more secure. The proposed crypto is first is because it has been reduced the number of iteration process. The proposed system can securely encrypt the medical as well as the natural images in an effective way. So what will be the scope in this region, in this area? So here you can apply the DNA level operations in a DNA, because the DNA level operation you can perform, so that will be more faster compared to the conventional way. And you can also think about the DNA based chaotic maps. That is the one of the reason where you can think about to, because the chaotic maps you have used, that is the basically the conventional chaotic maps. But if you want to realize this kind of chaotic maps and DNA levels, that you can think about. And here you can think about the DNA based keys, and these particular things you can also realize, so that the DNA based compression can be adopted in this particular process, so that you can store the data in a huge volume of data in a long term. So that is the area where you can work in these particular things. Okay, so that is the one of the objective. That means how to protect the confidentiality of the image content. So that particular part we have covered. Now we basically talks about the another area that is called the digital image watermarking. Now why the digital image watermarking is essential? Now thing is that suppose I have a content and I have shared the content to you in a secure way. Now what happened? You can decrypt it and you get the original content. Now the thing is that you can misuse the content. You can redistribute the content to someone else. Okay. Now once the content was decrypted, so there is no way to control the owner. Owner have no control to control the originality of the content. Now what happened? The receiver can modify it, he can redistribute it, and he can claim the particular content is his or her. Okay, so that is the one of the limitations. So that means to protect such kind of security threat, we need some kind of copyright protection. So copyright protection, the main objective is that we basically insert a copyright, but we insert a watermark, and if you distribute the watermark content to someone else, the someone else will not unable to change the content. So if you change the content drastically away, so then it will remove the copyright. So definitely, but there it is not the meaning to use that kind of content. The receiver can modify the content in some meaningful way so that they can claim it, but it is unable to do it because if suppose if you have a copyright is embedded with it, so then it can do it. So that is the main objective in this particular process. So once the data is decrypted, the security threats comes from handling the data. The threats may be occurring in terms of illegal copying and unauthorized manipulation of the data. So due to these regards, we need some kind of efficient algorithm that can protect the copyright ownership of the content. Okay, now here, just a minute. Now, digital watermarks. So in this particular process, what happened? We basically design digital watermarks. What happened? What way? Invisible patterns are embedded into the image, audio, or video. Sometimes visible patterns may be there, but we people basically prefer to invisible patterns. That means if it is invisible pattern, that is quite robust and quite more secure. Okay, and now you have invisible patterns that will be embedded into the image or video, audio, video. Now here we basically do the two things. How can we embed these particular things? Yes or no? Because we are embedding something your original content. So that means we are changing the content. So naturally the image content will be degraded. So here there will be trade-off. So how much you can embed it and what we can embed it so that the visual quality will not be compromised in a drastic way. Okay. So the process of embedding of a digital image as the image authenticity changing is perceptual quality. So that is the major concern in this particular process. So here, what is the purpose of a digital watermarking? We can preserve the copyright, and another we can preserve the integrity. So that we basically discuss in the later. So there is basically the three types of watermarking application is there. One is called the robust watermarking. And in the robust watermarking, what happened? Now you have your original image, you have a watermark, and you just simply embed it. That is the plus means you are doing the embedding process, and you are getting such kind of content. So from a human visual perception, it is quite difficult to guess that something content is hidden in this particular content. Now, what happened? I have done some kind of modification. The modification is like this. Here I have done this modification. Yes or no? So I have done some kind of modification here. Now in this particular process, if I have extracted, so I am getting this kind of content. So that means my logo is intact with this content also. So that means I can say that this is my the particular content is with me, ownership with me. So that means you are unable to destroy the copyright of this particular content. Okay. So that is the one of the way you can design the robust watermarking. Phrasal watermarking, that is also the one of the part of a passive forensic, active forensics, and that is also the main objective of a phrasal forensic. Phrasal watermarking is to protect the integrity. So what do you mean by the integrity? Integrity means if you have a content, if it makes some kind of changes your content, then you can easily detect it that there is some kind of malicious changes has been done. And then you can raise the warning to the user that the content was modified. So that is the objective of a phrasal watermark. So phrasal watermark, you have this logo is embedded and you are getting these things. And now suppose you have changed this particular content in this way and you are extracting this kind of thing. So that means you are unable to extract your original logo. So that means you can say that this particular content was modified. Okay, suppose I am sending some content to my friend. Now my friend should try to extract the logo, and if suppose he not get my logo, then you can say that the particular image was not actually coming from me. It was destroyed by someone else. So that's why you can preserve the integrity property in this particular process. Okay. Now, Another is the semi-phrasal watermarking. So semi-phrasal watermarking is basically preserve the certain property of the robust watermarking. Means certain kind of changes can be allowed, but it does not allow the drastic changes. And it also preserve the phrasal watermarking properties. So that means like this, you can change that your phrasal watermarking properties should be preserved in this particular process. Now, this is the generic architecture we basically follow to design any kind of watermarking algorithm. So what happened? You have original content and you have a watermark, and sometimes this watermark embedding process can be realized based on a secret key, because you know the particular process. Okay, other people don't know the what key is used in this particular process. Now, here the main contribution in this particular area is that what kind of embedding process you want to realize. Yes or no? Because you know there is a trade-off. If you embed the more watermark bit, so image quality will be degraded. And if you use the less watermark bit, then it will come under the security threats. So that is your challenge to how to design more robust watermarking scheme. And here the main contribution will be your watermarking embedding process, with the intention to preserve your visual quality will be good as much as possible. Now, generally what happened? You are transmitting this content to the internet, and the internet attacker can capture this particular thing. They can do any kind of attacks, and the receiving end, if you can recover the particular watermark, then you can say that your purpose will be fulfilled in this particular process. So here, this is the property, that is fidelity of robustness. If you give the more importance to the visual quality, your robustness will be compromised. If you give the more emphasis on the robustness, the visual quality will be compromised. So we can say that an ideal watermarking system should embed an amount of information that could not be removed or altered without making the cover object entirely unusable. The watermark should not be placed in a perceptually insignificant region. That is a very important point. That means it is not like that you can embed the content insignificantly, because you know that we basically prefer to transform the content in a compressed form, because image multimedia data like image video data is quite huge. Yes or no? So you need basically store the content in a compressed form, and accordingly that means, and compression basically carried out based on the removing with the redundant components. So redundant means it basically try to remove the insignificant component. So naturally you don't hide the content in insignificant region. If you hide the component in insignificance, so there is a highly chance your watermark will be easily removed. So if you hide the content in a significant region, so naturally that visual quality will comes under the threat. Okay, so that is the one of the reason in this particular process. Okay. So here you want to how you can design a robust, that is one of the area, and blind. So there is a two types of algorithm is there. One is called the blind watermarking, another is called the non-blind watermarking. Blind में क्या होता है ना, in case of blind, we basically don't need the original watermark, original cover media to identify the things. And naturally, this is the common scenario. Suppose I have a content, I have embedded some watermarks, I basically distribute to you, and you don't have the original watermark, you don't have the original content. If you have original content, you can modify it, you can change it, and you can put another watermark, and you can claim that that is mine. So generally, what happened? The receiver have no original content. The receiver have no original content or original watermark. So if you don't have the original watermark, original content, so in that particular process, the watermark extraction process is basically known as a blind watermarking process. And blind watermarking process is quite challenging process. Okay, so you people get the several watermarking process, but the nature of this kind of watermarking is basically non-blind. So if there is a very less what in the blind watermarking. So blind watermarking is a very challenging in this particular process. Now robustness. Robustness is that the attacker can change it in a meaningful way. And if you can drastic change, so that is no meaning. Suppose I have a content, and if I change the content in a drastic way, and that will not fulfill my goal. Just a minute. So here we basically discuss the how can I design the robust and blind watermarking scheme. So what is the motivation to develop a robust and blind watermarking scheme? In the blind watermarking approach, the original watermark, original cover media is not required. The blind watermarking scheme are more effective than non-blind watermarking scheme, since the watermark can directly identify without considering the original watermarks. The main aim of robust watermarking is to reduce meaningful digital data manipulation from any evildoers. Here, the extracted actual by experiment remains intact even after any attacks. As a result, the copyright property of the digital data should be retained in this particular process. Now, here, engineering, whenever you want to design a robust watermarking scheme, we have to choose some suitable transformation tools. The transformation like the discrete cosine transform, or you can use the DWT, discrete wavelet transform, singular value decomposition like this. Now, here I basically show one of the simplest way how can I design the one of the algorithm that is based on the discrete cosine transform. Now, whenever you apply the discrete cosine transform in a block level, suppose your block level size is 8 by 8. Then we can define the blocks after applying the discrete cosine transform in the block level. The coefficient basically arranged according to the significance in this particular zigzag scanning order. That is called the zigzag scanning order way. The coefficient will be arranged. And in generally, what happened? This particular this region is basically considered the insignificant region, and this is the insignificant regions. And in between is known as the middle band. Now, generally, what happened for the compression purpose, we basically simply discard the insignificant region. That means this particular regions are simply discarded. And here the thing is that if you change the something in a significant region, that will cause the drastic changes of your image content. So that means we people don't touch this particular region. Okay. Now the area where you can hide the content is the middle band. So that is the one of the middle band is shown in this particular process. The middle band is one of the area where you can apply, you can modify, and that modify will not be that much effective in a visual aspect. And also during the compression process, that particular content will not be removed in this particular process. So in general, the transform domain-based watermarking schemes are more effective than the spatial domain watermarking scheme. In the transform domain watermarking scheme, the cover media is transformed by suitable transformation tools. Now, the more standard algorithm basically use the hybrid transformation tool to make it more robust in this particular process. Now, in this particular algorithm, we have used the repetition code. So repetition code means suppose the information bit is 1, I have converted to information bit a code word of 3 bit. Suppose the information bit is 00 and this is the 00. If the information bit is 1, I have considered it 3 times of 1. So that means this is the repeat of the same content. If it is 1, 00, so then I basically map in this particular way. That is 5 times of 0. If it is 1, I'll map to the 5 times of 1 like this. Now, what is the advantage of such kind of repetition approach, repetition code? Now, suppose if we receive the 001, now here the decoding is basically carried out the majority of voting. So that means if you have a 001, if we take the majority of voting, so according to the majority of voting, so you can see that the majority is 00. So that means I simply decode my content as a 0. Okay. Now suppose you have another way. If you have a 0, 1, 0, again if you take the majority of voting of this particular way, you get the majority voting is 0. So that means you can decode the quantity 0. So that means you can perfectly decode it. So whenever you talk about the 3, 1, if you take the content is 0, 1, 1, according to majority of votings, you will get the wrong message, because actual the message was 0, 0, but you have a modified the 2 bit, so you are getting the wrong outcome. So that means according to the 3, 1, this is called the N, K 3, 1 repetition code. We have basically the error correction capability is single bit. So that means single bit error can be detected. Single bit error can be detected. But you have a more than a single bit error, suppose you have a 2 bit, so then it will not do 1. Similarly, if you are working with the 5, 1, so 5, 1, what happened? If your message is 0, 1, 0, 0, 1, so that means according to the majority of voting, you will get the outcome is 3. So that means you can say that your bit is 0. So that means 5, 1 can manage 2 bit of error correction. Okay, so this is the way. This is the meaning of error correction. Now, in this particular algorithms, what happened? Now we have taken the image. The image is decomposed into block level, and each block we have applied the discrete cosine transform. And according to the zigzag scanning order, we have selected some middle band coefficient. And here we have taken the watermark image, and this watermark will be embedded in this particular one of the algorithms. And here, this is the algorithm we have considered. Now, what is the algorithm? Now, in this particular process, we have taken the middle band coefficient. Suppose the middle band coefficient, this is the coefficient X and this is the coefficient Y. And this coefficient is so correlated that if you can modify this content, that will cause the less effect in your original content. Now, what happened? If suppose my water bit is 1, we basically change the relation between X and Y, X and Y. And if is X greater than Y, then we basically make no changes. Otherwise, we basically change the content like this, Y, X. So that means you just simply change it. So, but in the reconstruction process, that will be the less impact in the effects on this kind of modification have the less impact in the visual quality. Now, we basically carried out this kind of process in a suppose 10 coefficient. So 10 coefficient will be divided into a pair of 2, 2, 2. So that means you have a 5. So that means single bit that will be embedded into 5 times in your coefficient block. In the receiving end, what happened? This is the algorithms. In the receiving end, what happened? We basically check the relation. Whether the first coefficient is greater than second coefficient or not. If this condition is true, then you can extract the 1 bit. If condition is false, we can extract the bit is 0. So accordingly, suppose in the extraction process, you have extracted like this 0, 1, 0, 0, and suppose you extracted like this. So according to the majority of voting policy, we can say that your bit will be the 0. So that means watermark bit will be the 0. So that is the way we have done this particular process. This is the results of the different repetition code. Like we have taken the 5 repetition code, 7 repetition code, 9 repetition code, 11 repetition code, and this is the histogram of this kind of. This means the histograms are quite similar to the original image. And this is the results. How much the water extractor watermark is closed. The extractor watermark is close to 9.88. That means if it is value 1, so that means perfectly closed. And if it is close to 1, that means it is highly acceptable in this particular process. And similarly, the image quality should not be degraded. In this particular process, we can observe that image is around more than the 30 PSNR. So that means the if a particular image having the more than 30 PSNR, that is also acceptable in this particular process. Okay, so this is the results. So results means what we can present the results. Now we have to perform different kind of attacks, and after performing the attacks, whether you are able to extract the content or watermark or not. Like here we have taken the Gaussian low pass filtering attacks, and here you can see that the watermark is not in exact watermark. This is the approximate watermark, and this approximate watermark is close to the original one. So that means I can say that this particular image belongs to this particular logo, the owner of this particular logo. Now this is the another attack that is called the histogram equalization, and again the watermarks can survive in this particular process. This is the sampling attacks. This is the results of a salt and pepper noise. This is the results of the average filtering attacks, and average filtering, the watermark is not, but still the watermark is recognizable in this particular process. Sometimes this is a cropping attack, that means this particular portion is cropped, and even you are able to extract in this particular way. Okay, so this is the cropping attack by the white pixels, and you are able to find out this kind of way. This is the JPEG compression attacks, and sometimes you have to choose some standardized attack that is called the star mark attack. Star mark has some predefined standardized attack is there. So if you have developed any kind of watermark algorithm, and whether your watermark algorithm can satisfy this kind of can survive this kind of attack, then you can say that your proposed algorithm is effective in this particular process. Okay, so what is the contribution in this work? A novel watermark embedding process. That means your embedding process should be the novel. That is one of the area where you can contribute. The team is found to resist several image processing attacks. Now, embedding will be the novel. Now, the second is the how much it is novel, whether it is satisfying the actual security concern or not. That means if you perform any kind of attacks, the attacks can be survivable on this particular process or not. That you have to recheck in this particular process. And again, the third final is that you should, whenever design, your scheme should be blind. That blind is more real application. If you consider the non-blind have some limitation, and you should be the robustness. That means it can preserve, it can survive any kind of attacks in this particular process. So what we can explore this particular area, you can select suitable hybrid approach so that the robustness property can be preserved more effective way. More challenges to protect the copyright the audio data, because the visual perception have certain limitation. But if you changes certain content in audio signal, in that case, you can easily detect that what are the changes is there in this particular process. Yes or no? Suppose if you can change some images of the Lata Mangeshkar ji, so then you can as a human visual perception, it is quite difficult the changes. But if you change the audio, and you can easily find out, no, this is not the voice of the Lata Mangeshkar ji. So that is a very challenging in this particular area. Okay. Researchers may think about the reversible watermarking, because reversible watermarking means sometimes what happened, the watermarking basically causes the permanent distortion of your original content. But in the medical science, medical data, this kind of permanent changes is not allowed. Okay, so then people basically select the non-region of interest, and there they basically embed the content. Now the thing is that if you apply the compression algorithm, so naturally there is a quite easy to remove it. Okay, but sometimes you can remove the content. So reversible watermark is one of the area where you can explore in this particular process. And another thing is the suitable error correcting base. If suppose some error may be occurred, and you can use the suitable error correcting codes so that you can effectively recover the watermark in this particular process. Like in this our cases, what happened? We basically use the we have basically used this particular error correcting code that is called repetition code. So repetition code basis we can effectively survive our watermark in this particular process. Okay. So still now we have covered the two area. One is the ecosystems to protect the confidentiality property. Next we have covered the robust watermarking to protect the copyright ownership of the content. Okay. So anybody have any questions? Otherwise we'll move to the image forgery. Any questions from these two area? Okay. So next we basically discuss the image forgery. Okay, so image forgery means what? Now this is the image content, and here this is the original content. Now what happened? I have copied it and I have pasted it. So that means it is basically the forged image. So act of tampering a digital image with the illegal intention. So that is basically forged in this particular process. The process of identifying the forged or tampered image. So that means if you made such kind of changes here, so then your objective will identify what kind of changes you have done in this particular process. So there is two types of forgery is there. One is called the active forgery, another is called the passive forgery. Active forgery means we basically embed some mark value that is called the certain prior knowledge about the original image required can be applied on the only those images which have undergone some pre-processing at the time of image creation. Like means we basically embed some watermark, and basis on that you can easily identify that whether the particular image goes any kind of attacks or not. Okay, but that means those images are generated by the originator, particular originator, then you can do this kind of things. But naturally what happens in the real world, the images are created by so many peoples, and every people's watermarks, it is quite difficult. So that means passive forensic is one of the area where it basically works in this way. It does not require any prior knowledge about the original content. It basically involves the forgery detection based on the raw image analysis, considered as a blind forensic or blind forgery detection. No specific passive forensic method can be handled all possible cases of forgery. Includes a variety of type-specific forgery detection scheme in this particular process. So that means passive forensic is quite challenging. Active forensic can effectively look at the forged region, but the passive forensic is quite challenging in this particular process. So let's see with respect to this particular process, the one of the active forensic, and subsequently we'll see the one of the passive forensics. Okay, so what is the problem statement in this particular process? Now, image authentication code generation is one of the area, and then you have to embed this particular code in a particular cover media, and accordingly you will get the watermark image. Now, if watermark image goes any kind of modification, any kind of changes, then you can easily detect the content where the particular content was modified. So that is called the temper detection, and temper localization is one of two areas we basically focus in this particular area. Okay. Am I audible to you? Is there any problem? Am I audible? Okay. Now, what are the objectives? Embed watermark should not be noticeable to the viewer. Watermark should not affect the quality of the original content that we already have discussed, and performing the fast accurate forgery detection. Okay, that is the one of the area where you can think about. And obtaining low false positive rates means it is the low positive rates should be minimized in this particular process. Now, what is the model architecture in this particular process? The model architecture like that, you have original content, you take the fragile watermark embedding, you design some fragile watermark embedding process, and then you get some watermark image. Now, naturally, what happened? This particular content will be transmitted to the public channel, and public can modify the particular content. Rifat, so here what happened, we have taken the watermarks, any kind of attack is possibly possible. That what kind of attack we have done? We have changes these particular things here. That means here we have changes this kind of things. Now, your objective will be to locate the forged regions. That means this is the forged regions I can effectively locate in this particular process. So what is the proposed word method? That is water embedding algorithms. Here basically the contribution will be like this. You have to design some suitable watermark embedding algorithms. and you also effectively identify the temper detection and also localize this temper design. Now, in this particular process, we have used the CRC code, that is cycle redundancy code we have used to create the watermark, and that watermark will be embedded in the original image using the LSB substitution method. Okay, so let's see with the example what way you can design these particular things. Like you have an image. First of all, divide the image into non-overlapping blocks, and we have taken a seed, and basis on seed, we basically create a random sequence. And this particular random sequence, what happened? We basically create. We take some more significant. That means pixel will be divided into two components. One will be the significant component and the insignificant component. Based on the significant component, we basically compute the cyclic redundancy code, and that cyclic redundancy code will be XORed with the key. So that means it will be perfectly secured by the owner. Now, this will be embedded into the LSB position, and accordingly you'll get the watermark image in this particular process. Okay, so like this, you have taken the 2 by 2 blocks. 2 by 2 blocks means you have 4 pixels. From 4 pixels, you have taken the 6 MSB position content. So that means the 24-bit content will be there. And if you apply the CRC 8-bit generator, so you get the 8-bit, and you just, based on the key, you just perform the XOR. And after that, you just substitute the two LSB methods, and then you get this kind of watermark bits. Like this is the one of the examples. Like we have taken, this is the MSB, 6 MSB we have taken, and basis on that we have obtained this particular row vector, and you have computed the CRC code. This is the 8-bit, and you have taken the another secret parameters, and you perform the XOR, and this is the component. And here we have divided the particular component into 4, again the 4 sub blocks, and that is the 0, 0. So that means this particular 1, 1 will be replaced by 0, 0. This will be 1, 0 will be replaced by 0, 1. This 0, 0 will be replaced by 1, 1, and this 1, 1 will be replaced by 1, 0. So finally, you can see that this is the modified component in this particular process. Now, what will be the extraction process? This is the CRC code. I hope you know it. I'm not going into details into the CRC code. Now, what will be the extraction process? What will be the temper detection process? Now, temper detection process will be carried out the same way. We basically take the 6 MSB, and we also extract the 2 LSB, and we XOR it, and we basically compare it. Whether both are giving the same syndrome value. If the syndrome value is 0 in the both cases, then we can say that there is no error. So that means you can mark it the particular pixel as a 0. And if there is an error, so you mark it as 1. Okay. So naturally, what happened? This is the way you can perform it. Like these particular cases, this is the image, and this is the watermark image. And suppose you have done such kind of changes in this particular process. So it is the received image, and this is the binary map. So the particular region, the watermark is there, and this is the final image. You can see this particular image is the plot in this particular region. Like this particular image, we have taken this and resized it and copied it in this particular region area. And you can easily find out this is the region where the particular image is currently available. Like this particular image is there. And here we have copied the image in a multiple and placed this particular position, and you can effectively identify this particular reason. Okay, and this is the changes we have done in here, and these particular changes you can effectively identify in this particular image. Like here, there is a one. It is removed here. This is another area where you have changes, this kind of changes like this, and these changes will be quite effectively you can look at in this particular process. Okay, like there is a one added in this particular process, and you can identify these things. Okay, just to see that you have tried to done some meaningful changes. Okay. Now, after these things, we have to measure the performance. The performance means the watermark should be protect the high visual quality. That means you have to measure the PSNR. And then we also compute the structure similarity, how much this particular content similar with respect to this particular process. So that means the structure similarity says the water image is close to 1 and you are getting the high PSNR value. So that is the highly secure in this particular process. And entropy analysis we have done, and that means that entropy difference. Entropy is the watermark image, entropy is the original image, and how much difference. If the difference is very small, then you can say that it is quite effective in this particular process. And true positive, false positive, and false negative, and basis on that you basically compute the accuracy, and your accuracy, the false positive rate should be quite close to 0 if it is the effective one. So what is the merits? It is the high forgery detection accuracy, high fidelity, very low false positive rate, efficient watermark algorithm as well as false detection process can be possible to design, and any form of forgery can be detected, can detect multiple forgery. But what is the limitation? Temper detection cannot be done unless the image has undergo watermark embedding process. Means until you have not embedded any kind of watermarks, you are unable to identify the forged region. Most of the image capturing devices lacks of functionality of watermark embedding process, so that is quite difficult to find out the real scenario in this particular process. Okay. So then what is the conclusion? The proposed scheme performs efficient watermark embedding and forgery detection, and blockwise watermark embedding results is decrease the watermark payload, encryption of watermark using random secret and the secret of randomness, and it having the high structure similarity values and also having the high PSNR value, and it is having the significant accuracy and low positive false rate in this particular process. Okay. Like in the real scenario, what happens? Suppose if we take the video data, if you store in a raw format, that means if you have a 90 minutes video and if you have a 90 minutes low quality video, that video can need more than 180 GB. So naturally what happened, we basically stored the content in a compressed form. Yes or no? So like whenever you capture the content, actually the video is basically stored in a compressed form, but actually your image is stored in a compressed form. Now if you want to view this particular thing, we need some kind of converter, a video reader, like a DVD player, different kind of player. So it basically perform the decoding process. Like a similar way, if you want to design a active forensic toolbox, and at the time of capturing the content, if it can embed the particular watermark, so then you can easily detect the any kind of forgery in a subsequent stage, in the later stage. So that means here you can think about such kind of algorithm in a hardware base, and if the hardware can detect the particular changes can be happen, and that happen, you can really effectively detect in this particular in the subsequent stage. Okay, so that means this is the one of the way you can design this kind of algorithms. Now we basically discuss the another area that is called the passive forensics. Okay, so now in the passive forensics, that is quite challenging in this particular process. Okay, so before going to the passive forensics, if you have any questions, you may ask right now. If you have any questions, you may ask.
Guys, if you have any question, you can write in the chat box so that sir can reply to your question.
Okay. So still now we have discussed the three area, that is image crypto system, robust watermarking, and another is the active forensics. And this is the active forensics is also one of the application of a watermarking, that is called the physical watermark. But the forgery of a passive forensic is quite a different approach, and it is quite more complex and it is more challenging process. Okay, let's see. This is the one of the original image, and you have intentionally removed this particular content from here. So what happened if you remove this content here? So that means you can prove that in that particular moment you are not present in this particular shopping mall. So that is the one of the, that means this is the tempering of your content. Now what you can detect this kind of things? Like this is the another area, popular image. Like you have a tanker that is, you are claiming that now I am not send the tanker in your region, but this image is fraud and you can claim like this. Like this is the one of the this is the call of image example image following by copy move forgery. This is the example of a copy move forgery. Another kind of forgery is like image compositing by slide forgery. So that means this is the common, this particular image, this is the original image, and this image was published in a Malaysian Delhi, and it is basically the forged image. This is the another example. This is the two different views, basically GIFs, but in a particular newspaper, these two separate images was composite, and it is created like such kind of forged image. This is another example, like you have image and you have changed the content like that. This particular scenario says that I was present in a daytime, but you are claiming that I was present in a night time. So that is the one of the area where you can think about. That is called the retouching. Hello. Hello. Sorry, friends. Okay, so like this, if you have a image, now am I audible to you now? So if you have original image, so image
Yes,
here
sir,
you
are
can
audible.
you can change like this way in this particular process. Okay, so this is called the retouching way. So that means there is a three types of forgery is possible. One is called the copy move forgery. One is called the image compositing. That means you can composite. This is quite challenging. Like this is a two different content is clubbed. This is the image retouching in this particular process. Okay. Now here active forensics is quite effective, that already I've discussed. Now passive forensics, what happened? Tempering likely disturb some intrinsic regularity. No need the prior embedding authentication code is there. No single passive forgery detection approach can handle all possible cases of forgery. So that is one of the limitation. So in this particular lecture, I basically show you one of the passive forensic that is based on the copy move forgery. So that is the one of the passive forensics we can basically discuss with respect to copy move forgery. Now, copy move forgery already discussed. What is the meaning of the copy move forgery? One of the base paper that is called the FIDGIS. FIDGIS is basically one of the base paper that was proposed how to handle the copy move forgery. But the thing is that the FIDGIS algorithm having huge computation over it. So that I told you, and subsequently we can how can I resolve this particular process that I can tell you later. Now, what is the process? Now you have an input image. The image will be divided into non-overlapping blocks, and we basically extract the pictures and from each blocks, and then lexicographically we basically sort these particular things, and we basically perform the similarity matching, and finally you get the map image. Okay. Now, what is the process? Just I want to show you with this particular example. Suppose this is my image background, and suppose I have a content like this. Now, what happened? I have copied this content and I have put this content in this particular region. Okay. Now, what happened? I basically compared the distance with respect to, this is one of the reason, and I basically compared this distance with respect to whether this content is similar to the all other, how many component, that basically distance I will show you. So what happened? This component distance is, this is the close, this is similar to this one, and this is the apart from D distance. Okay. So right now what happened? I basically count with respect to apart of D distance, how many pixels are similar. So here you can see that similar structure you have copied from here to here. Naturally, what happened? This distance will be preserved. So that means this content and this content, they are basically apart with D distance. Now, similarly, if we compare this distance, and again this distance is also similar, and again this is close to differ by the D distance. So that means with respect to D distance, how many pixels are more close? So naturally, if we copy this particular content from here to here, naturally we basically gives the more similar content, and here the maximum, there will be maximum peak here. But it may be like that. Suppose you have another content here, and this component is captured here, and this is basically apart from D1 distance. So that means from D1 distance, from D1 distance, you have another peak. So that means here I can see that this is the one of the reasons where you can forge, and this is the one of the forge. That means those two similar contents are copied from this to this or this to this, very much way. And this is the reasons where it was copied from here to here and here to here. Okay, so this is the, so that means here we basically measure this particular algorithm based on the distance. That means when a particular distance, how many similar pixel component, but how many block level similarity is preserved. Now here we basically perform the exhaustive search. So naturally the computation overage is very huge. So FIDGIS later what happened? They basically, instead of comparing the pixel to pixel, they basically start to compare basically based on some salient component, and they have used like the discrete cosine transform. And accordingly, they have reduced the some computation over it, but this particular algorithm having the huge overhead. So here we want to propose one algorithms that is called the improved reduced feature vector based copy move for the detection techniques. And here we basically follow this kind of algorithms. We have initially taken the static wavelet transformation that basically capture stationary wavelet transformation that basically capture the invariant features. So that means it is not like that the particular one orientation image will be obtained. You can find out the different orientation content you can find in this particular process. Now subsequently you can overlap these particular things and you extract the features, and that features will be now the main contribution in the proper feature selection. So that means right now my algorithm will be, my problem statement will be changed from originally from the feature selection process. That means how we can select the more efficient feature in this particular process. Now after that we basically construct the feature matrix, and then feature matrix will be sorted, and subsequently suppose we have taken the similarity matching. So not rather than matching the similarity whole content, we basically select by component wise, and if they are dissimilar, we subsequently basically discard it, and if they are similar, we basically map it and accordingly create a binary map. And finally, we can perform the different kind of morphological operation to remove those kind of unwanted components. So this is the one of the results. So like this particular component copy from here to here, and this you can easily detect in this particular process. Like this is the one of the component is here, copy from here to here, and this you can easily identify this. This is the component is copied from here, you can easily identify this. Like this is the component, you can easily identify this. Now what is the major contribution in this particular area? Now features computation, the feature dimension is 64, where feed is that is the DCT base having the size is 64. Another SBT base is there. They basically use the 20 block size, and the feature dimension is quite is that, but the accuracy is not that much effective. Another area that is the hybrid is used, but the feature dimension is quite 16. But here in our proposed area working principle, we have taken only the 3 components, and that 3 component is effectively works in to identify any fault station. So that is our objective to design this particular algorithm. Okay, so overall we can see that even our algorithms can effectively works with the small size of feature vector, and it can effectively find out the accurate results, and it having the less false positive rates in this particular process. So what will be the contribution in this particular design? The particular contribution will be like this in particular area is that how to identify the proper features. The proper feature selection is the one of the area where people can focus. And here that distance measure. So here you have to, instead of comparing the distance in a conventional way, if we can use the tree structure distance measurement, that can effectively reduce the computation overhead. That is the one of the area where you can do. And finally, to get that, there you get some false positive area that can be removed by the morphological operation, and you can finally get the desired results. That desired result shows that that particular image is properly caught in this particular. Okay. So any questions? Any doubts? So now it is open to discussion.
Guys, if you have any question, you can write in the chat box, or else you can unmute yourself. You can ask the question directly from chat.
So is it fine? Actually, I have covered the all the area and where you can do some kind of contribution. So that means, as per your theme of your workshops, that how can you protect the multimedia data like image, because image is a very huge volume of data. So we have covered the confidentiality aspect, we have covered the integrity aspect, and we have covered the copyright protection. And that means authentication aspect we have covered. And finally, one of the area that is very challenging, that is called the passive forensics. And here we have basically discussed only the copy move perjury area in this particular lecture. And I hope you'll get the more idea how to work in this particular area.
Yes, sir. Thank you so much, sir. It was very nice presentation and content was also very good. Thank you so much for accepting our invitation. Thank you, sir. Thank you.
Okay.
So, Murli, sir, we can end this meeting now.
Okay. Thank you.
Thank you, sir. Thank you.
So, shall I?
Yeah, sir. Yeah, sir. Thank you so
Bye.
much, sir. Murli, sir, we will meet at 3:10 for the next session. 3:10 p.m. Huh? Okay.